The electrochemical nature of aqueous corrosion.
What is an aqueous corrosion? Aqueous corrosion is an electrochemical reaction of materials due to a wet environment, resulting in the deterioration of the material and its vital properties. So basically, it is a type of corrosion in a wet setting. These are the examples of an aqueous corrosion. There are different forms of aqueous corrosion, one of which is the pitting corrosion. A pitting corrosion is an extremely localized form of corrosion that occurs at inconsistencies in the steel surface, such as coating, holidays, or breaks in passive films. Pitting is typically characterized by small holes, greater in depth than diameter. As you can see from the figure, there are holes present in the material. This is due to coating holidays or the inconsistency of polishing the particular type of material. In this case, a steel pipe. Another example of a pitting corrosion is the pitting of mild steel reinforcing bars in a marine environment. The next form of aqueous corrosion is the crevice corrosion. Crevice corrosion typically occurs at the interface of two surfaces. Such interfaces might occur at the meeting of two plates, at the base of a bolt head or the edge of a non-metallic coating or wrap. From the word itself crevice, thus it creates a narrow opening that results to a crack, a split, or a so-called fissure. As observed from the figure, there is a narrow opening between two different materials, which is the wall and the hollow surface. The narrow opening in between is the so-called crevice corrosion.
Another example of a crevice corrosion is at a perimeter of a flange fitting. Another form of an aqueous corrosion is the filiform corrosion. This form of corrosion can often be seen on painted alloy engine components working in harsh industrial environments. The thread-like corrosion can appear on coated metals, such as steel, iron and, even zinc. The corrosion of the painted metal or alloy happened due to the presence of the air, the water, and to other factors which is considered harsh in the environment. The last form of aqueous corrosion is the galvanic corrosion. This is the most basic form of aqueous corrosion. It is also known or called as bimetallic corrosion. This occurs when two dissimilar metals are placed in direct contact, or are otherwise electrically connected, in the presence of a conducting solution. The more active of the two metals is anodic, with respect to the other, and corrosion of the active metal is likely to proceed. As observed from the figures, there are two different metals in contact with each other. And one of the two metals is considered active, and the active metal will probably experience corrosion. Another example of a galvanic corrosion is the mild steel bolts, coupled with stainless steel plate. Aqueous corrosion is electrochemical in nature. When we say electrochemical corrosion in nature, this occurs when two metals with different electropositivity come into contact with an electrolyte, or a liquid medium. As presented from the figure, there are two different metals, in contact with each other, placed in each test tube, and submerged in a so-called electrolyte. The more electropositive element is corroded and the less electropositive element is protected from corrosion by the more electropositive element. So this simply means that if one of the two metals in contact with each other, and is submerged in an electrolyte, is more electropositive, then it will probably experience corrosion. The other metal on the other hand, which is the less electropositive, will be protected by the more electropositive element against corrosion. For us to be able to know the electropositivity of an element, a diagram is introduced. This diagram contains a set of elements which are most commonly used in creating or making engineering materials, that can be used in the engineering industry. Now let us consider this example, the rusting of an iron nail. As presented, this is an example of an electrochemical setting wherein two metals in contact with each other is placed in each test tube and submerged in an electrolyte. In this case, the agar plus potassium hexacyanoferrate solution plus phenol phthalate indicator will serve as our electrolyte. From the first test tube, we can see that the iron nail is wrapped around by a magnesium ribbon. Based from the electropositivity diagram, we can identify that the magnesium is more electropositive than that of the iron, which is less electropositive. In this case, the magnesium ribbon will most probably experience the corrosion, and the iron nail is prevented from rusting. On the other side, we can observe an iron nail being wrapped around by the copper strip. And in this case, the iron is considered more electropositive than that of the copper strip. Thus, the acceleration of rusting the iron nail will eventually proceed. Since it is electrochemical in nature, thus it involves the flow or exchange of electrons, which constitutes a reduction and oxidation, or the redox reaction process simultaneously. And we will be able to identify the anodic and cathodic reactions. For example, if zinc Zn is placed into hydrochloric acid, HCl, zinc chloride is formed, along with hydrogen gas, H2. To balance the equation, we are going to add a base 2 beside the HCl, and an hydrogen gas, H2, on the right side of the equation. The equation above can also be written as this one. Since 2Cl is located on both sides of the equation, we can cancel it out. Then this will be our final balanced equation. From this equation, we can now be able to identify the anodic and cathodic reaction. This is the anodic reaction. And this is the cathodic reaction. So what is an anodic reaction? An anodic reaction is an oxidation process through which the valence of a metal increases from 0 to a more positive value. And since it undergoes an oxidation process, as the valence increases, the metal itself will become the negative terminal of the exchange and flow of electrons, and thus electrons present in that particular metal as being released. Thus, in an anodic reaction, there is a loss, or release of electrons. So there are two main types of an anodic reaction. These are soluble corrosion product, which does not protect the surface of the metal, and solid corrosion product, which may or may not slow the corrosion of the metal. We can obtain both of this corrosion product in a particular equation of an anodic reaction. To identify the corrosion products, we will make a general representation of elements. To generalize, we let M be any element, and N be the number of valence or coefficient. In this particular form of equation, which M equals Mn raised to the positive, plus Ne raised to the negative, we can automatically identify that the soluble corrosion product is Mn raised to the positive. Now in this form of equation, which is the combination of the elements equation, we can obtain that the solid corrosion product is M(O) subscript of N. From our previous example, we have the zinc added hydrochloric acid, yield zinc chloride. In this particular form of equation, by applying the general representation of elements from the previous slide, we can easily obtain that the soluble corrosion product is zinc with 2 valence electrons. And from our original combined equation, we can identify that the solid corrosion product is zinc chloride. From the image representation at the left side, we can imply that aqueous corrosion involves the loss of metal to the aqueous phase. And when this occurs, the metal releases a number of electrons into the metal or alloy. So the zinc metal from the anodic reaction will be able to release electron, and thus will eventually result to corrosion. Now let us proceed with the cathodic reaction. A cathodic reaction is a reduction process during which the valence of the species is reduced. As the valence of the element is reduced, the electrons from the anodic reaction is consumed in the cathodic reaction. Thus, there is gain of electrons. The electrons produced during the anodic corrosion reaction must be consumed at the same rate by a corresponding cathodic reaction. Cathodic reactions consume electrons and are reduction reactions. Thus, the valence is reduced to a lower value. From the image representation at the right side, we can imply that, as the metal or alloy consumes electrons, the electrons will flow to the metal or alloy, gained by hydrogen and water, to form hydrogen gas at the cathode. There are two cathode reactions in the natural environment. One is the hydrogen evolution reaction or the HER, wherein in this reaction, a 2H raised to the positive accepts electrons to become hydrogen gas. The other one is the oxygen reaction reduction or the ORR, wherein oxygen in water is reduced to form hydroxyl ions. And that would be all for the electrochemical nature of corrosion. Thank you for listening. Hope to see you next time.